All right, guys. In this section this week, we're talking about the normal distribution. Now, first off, a normal distribution is kind of the spread of data that you've collected. And a normal distribution is one where most of the data is centered around the mean, and then it kind of tails off in either direction the further away you get from the mean. So, for example, this first chart shows pizza delivery times, and it looks like the mean would be about 64 minutes if you look closely at that chart, because it's in the middle and it's the highest. So most of the values are going to be centered around that mean of 64 minutes. So a lot of times might be slightly off, like 63 minutes, 65 minutes, but most of them are around 64 minutes of the mean. And you have fewer and fewer pizza deliveries that extended above that time and below that time. So the further away you get from the mean, the fewer deliveries that took that amount of time. So for example, there's very few deliveries that took 71 minutes, 72 minutes, and longer. And there's very few deliveries that took, 59 minutes and 58 minutes, because they were shorter. But most of the deliveries were spot on around the same time of 64 minutes. So normal distribution has that curve to it. Most of the values you've collected are going to be centered around the mean or close to the mean, and you're going to have a lot fewer kind of outside of that mean, kind of near the left or the right end. So things that are normally distributed would be things like these pizza delivery times. They also have a list down at the bottom. I think of, I don't know, but there's heights, for example, are distributed normally. And there's a few that we'll walk through in this video. But before we get into a lot of it, I kind of want to give you a brief rundown on what this normal distribution curve looks like. So in this graph that you see here, the red curvy line is our distribution. As you can see, it's higher near the mean, which is in the middle. And by the way, just so you're familiar, that little funky U-shaped thing, that means mean. Okay, so that's your average. So just a heads up, that little U with a squiggle thing, it's called mu, stands for mean. And the other symbols that you see that looks like this, oops, I can make it look a little bit better. That stands for your standard deviation, okay? So notice how I've broken this down. I put the mean right in the middle, right at the peak of that curve. And then off on the left and the right, I've gone one standard deviation to the left, so -1 standard deviation, one standard deviation to the right. And then -2 standard deviations to the left, 2 standard deviations to the right, and -3 standard deviations to the left, 3 standard deviations to the right. And they're all equally spaced apart. They're not going to be, some closer together, some not. The standard normal curve, which I've listed in green, I kind of wrote the annotation in green, would have 0 as the mean, so 0 right there in the dead center, and then 1 as its standard deviation. So 1 would be 1 standard deviation, -1 would be 1 standard deviation to the left. -2 would be 2 standard deviations to the left, +2 would be 2 standard deviations to the right. -3 would be 3 standard deviations to the left, and a +3 means 3 standard deviations to the right. So just know that this is kind of the layout of it. There's a little more we're going to add to this probably near the end of the video, but that's just kind of a brief rundown of some things. But what does all this even mean, right? Well, let's talk about it. Let's go back to our graph of the pizza deliveries. Now, I don't really want to stick to the pizza deliveries too much. I kind of want to look at the example they have here. So in this example, adult female heights are normally distributed with a mean of 64 inches and a standard deviation of 3 inches. So how this is going to look on the graph, and you can see the graph laid out there, is since the mean is 64, that's our average, the mean in the middle, 64 is right in the middle. You're going to see it right there at that peak. Now, since the standard deviation where was it? Standard deviation was 3 inches. That means one standard deviation to the left will be 3 inches less than the mean. So that's why it's 61, because that's going to be 3 inches away from the mean. One standard deviation to the right would be 3 inches away from 64 to the right, so 67 inches, right? So standard deviation is 3 inches, means that each standard deviation is going to be 3 away from the next. So 67, 70, 73, right? And same thing on both sides, the left and the right. So one standard deviation to the left would be 3 inches smaller than 64. 2 standard deviations to the left would be another 3 inches smaller than that. So that would be 6 inches from the mean in total. It's 3 inches and 3 inches. And then if you want to go 3 standard deviations from the mean, that's another 3 inches away, which would be 9 inches in total. So that's standard deviation is kind of the spread of the data, remember. It measures how spread out the data is. And for a normal distribution, that's what it looks like. Okay, so the mean is in the middle, and then 1 standard deviation, 2 standard deviations, 3 standard deviations. Obviously, the mean can vary depending on your data, and the distance of the standard deviation can vary depending on the data as well. Okay, but that's how that graph gets laid out. If you look at example 2, let's draw this before we actually see it. This one has the mean as 1,500 calories with the standard deviation of 150. So if we were to draw a sketch of this curve, we would have the mean of 1,500 in the middle. And since the standard deviation is 150, one standard deviation to the right would be 150 more than 1,500. So that would be 1,650. 2 standard deviations would be another 150. So that would be 1,800. And then 3 standard deviations away would be another 150, which would be 1,950. To the left, we'd have 150 below for 1 standard deviation to the left. So that would be 1,350. Another 150 less than that would be 1,200. And another 150 less than that would be 1,050. So this is our mean in the middle at 1,500. Then we have 1 standard deviation away. Then we've got 2 standard deviations away. And then we have 3 standard deviations away. So the curve would look something kind of like this, be at the peak in the middle and drape down near the end. So the mean's in the middle, and then you've got your 1 standard deviation away, 2 standard deviations away, and then 3 at the very end. So that's what the graph would look like. And when we go here, you can see there it is, right? 1,500 in the middle, and then 150 separating the first, second, and third standard deviations. Okay. Now, just to quickly answer this about the curvature, how does standard deviation affect the shape of a normal distribution? Well, again, a normal distribution, regardless of whether it's the blue line, red line, or green line here, they are all normal distribution because they are all centered at the middle and they kind of tail off to the left and tail off to the right. But they look different, right? Some are peaked higher than others. So if the standard deviation is small and there's less variance, in the sense that it's not that spread out, you're going to see a graph like the blue line, where it's very tall in the center, and then it gets, it's very flat on the ends, because most of the data is going to be collected right near the middle. If you have a standard deviation that's rather large and spread out, then you'll get something like the green line, where yes, you have most of it in the middle, but because it's so spread out, you're going to have lots of data on the left and on the right side as well. So it's still a normal curve, it's still a normal distribution, but you're going to notice that the curves can be slightly different depending on how spread out it is. It's still, standard deviation still measures how spread out the data will be. Okay. So let's get into, I want to see if there's anything left on this slide I want to talk about. I don't. Let's get into page 2. So now we're going to talk about probability. So this is rather interesting. And if you have a graphing calculator at home, you're going to love this. This will be perfect. If you don't have a graphing calculator at home, no worries. It's still just as easy for you to do. There's a link down here at the bottom called a Z table for your notebook. You're going to want a copy of that. I already have it opened up here. And we'll use it. I'll show you how to use it. Obviously, it's a lot of numbers, but it's just a little table, just a little chart that you'd have to go kind of looking for the number that you need. I'll tell you exactly how we're going to use that in a second. So let's look at this example. So Gustav's pizza dilemma. He can order from DeLuca's Pizza with a mean delivery time of 32 minutes and a standard deviation of 5 minutes, or Vinny's Pizzeria with a mean delivery time of 31 minutes and standard deviation of 6 minutes. He wants to be sure that the pizza will be delivered within 30 minutes of ordering. What's the probability that each pizzeria will deliver the pizza within 30 minutes? Okay, so I believe it might work the whole thing out here, but let me kind of just show you what we're going to have. So there's two pizza companies that we're comparing, so we're going to make two charts. First one we're going to make is for DeLuca's Pizza. So for DeLuca's Pizza. Now, DeLuca's Pizza had a mean of, I think it was 32 and a standard deviation of 5. But let me check that again. Mean delivery is 32 and standard deviation is 5. Yes. So his graph, his chart would look like this. He'd have 32 in the middle. And since standard deviation is 5, one standard deviation would be 37. Because it's adding 5 to it, then add another 5, be 42, and then 47, right? If you go to the left, standard deviation would be 27, then 22, and 17. So the curve looks something like, well, let me see if I can start in the middle. So the middle is 32. So the curve can look something like this, right? Now, we want to know what's the probability, that his pizza will be delivered within 30 minutes. So 30, roughly based on our number line, would be about here, right? Let me put this in red so it stands out, right about here. So this is where 30 would be. Now, the area of this curve from 0 minutes, which would be way at the end over there, that's kind of off the screen, right? From 0 minutes all the way up to 30 minutes. This entire area is the probability of our pizza being delivered within 30 minutes, anywhere from 0 to 30 minutes. So this shaded area in red. So we want to find the area of that. Now, the good news is we really don't have to do too much math. There's no calculus involved that we would normally have to do from scratch. We can do this with our Z table or our graphing calculator, whichever one you want. So let's start with if you don't have a graphing calculator. If you don't have a graphing calculator, you're going to need to use a quick formula. The formula is going to be to find something called the Z-score. And so here's the reason we have to use this. So this distribution, notice its mean is at 32 and its standard deviation is 5. But a standard normal graph, remember a standard normal had a mean of 0 and a standard deviation of 1, making things very easy for us because 0 being the number right in the middle and then 1 being one standard deviation made a lot of sense, right? So basically what we're doing is we're converting this information from the number line into a normal distribution. And then that's where the table is going to come in handy. So the Z-score, again, this is for non-calculator folks. So if you don't have a calculator, you're going to use the formula for Z-score. So it's going to be x minus the mean divided by the standard deviation. So x is going to be the value that interests you, in this case 30 minutes, right? So x is going to be 30 minutes because we're looking for the probability of 30 minutes, minus the mean. So the mean was 32. Remember the mean, the average was 32. We wrote that down earlier. And then our standard deviation was 5. Okay, so we're just going to quickly calculate that out. So this would be -2 divided by 5, and that comes out to be -0.4. Okay, so now keep this number in mind, okay, -0.4. So if you clicked on that chart, right, here's our Z-score. So you're going to look on the left side here. Can I draw on it. I don't know if I can draw on it. I might be able to. No, I can turn it around though. Okay, can't draw on it. That's fine. So you're going to look on the left side, those bold letters for negative 0.4. So it's near the bottom. And now the numbers that are in that row go on the second digit. So since our number is negative 0.40, because negative 0.4 is named negative 0.40, when you go look at that table and you look at the top of that table, right, the top number is the 0.00.01 is the second digit. So since it's 0.40, we're going to look at the very first row at that. So negative 0.4 in the first row we have says negative 3, or I'm sorry, says 0.34458. Is 0.34458. So this is our probability, just like that. We've answered the probability 0.34458. Just to quickly tell you what the rest of that table was. Let's say, for example, our z-score ended up being like 0.47, negative 0.47, just to show you how to read this a little bit better. If it was 0.47, I'd go to the negative 0.4, the same row I was at, but then I'd go over to the 0.07 part. So that's going to be, if you can look at the top, again, I can't write on it, unfortunately, but on the top row where it says 0.07, you're looking at that column. You're looking for where those two meet. So that column meets where, that row at 0.31918, because that's where that row of negative 0.4 and 0.07 meets the 0.31918. So that's if the probability was 0.47. I just wanted to show you that in case you needed to read it. But since ours is 0.40, that's why we looked at ours and we went to just the first column, because first column was 0.00. So 0.40 is just the very first number there. Right? So this would be, 0.41, this would be 0.42, 0.43, 0.44, etc. Okay? Just to kind of help you see that a little bit better. So there's your probability. Now, if you have a calculator, okay, here's what you're going to do. If you have a graphing calculator, you're going to hit second and vars. Okay, it's going to take you to your distribution. Then you're going to go to normal CDF. And here, you want your lower bound as this negative 1E99. Basically, this basically means negative infinity. So since our number, or you can put, in this case, I guess 0, because we hit going from 0 minutes to 30 minutes, you can leave it as 0. So we'll leave it as 0. Upper bound was 30, since we wanted the delivery time between 0 and 30 minutes. The mean was 32, and standard deviation was 5. Remember, that's given to us in the problem. And so with all that information typed in, we calculate it and we get the same result, right? 0.34458 when you round it. So the calculator works this way. So rewind the video if you need to see those steps again. But there's our probability for the first one. Now we need a probability for the other company. So the other company was Vinny's Pizzeria. So Vinny's mean was 31 minutes and standard deviation of 6 minutes. So mean was 31, standard deviation is 6. So his graph would look like this. He'd have 31 in the middle, and then standard deviation of 6. So it'd be 37. Add another 6 would be 43. Add another 6 would be 49. Now the standard deviation below this would be 25. If you subtract the 6, 19, and 13. So his graph would look something kind of like this. Now we're still looking for the same thing, the probability of less than 30 minutes. So 30 would be right about here, right? And probability of less than 30 minutes means the area of the curve less than 30 minutes. So all the way from where 0 would be for 0 minutes all the way up to 30. And so again, if we're going to do this by hand, we're going to use our z-score. So remember the formula, okay, is x minus the mean divided by standard deviation. So x is going to be 30 since we're looking for a 30-minute delivery, minus the mean, which is 31, and the standard deviation in this case was 6. So 30 minus 31 is -1. -1 divided by 6 is -0.16667, we'll say, rounding it to be repeating. So that is a negative number. So now we're looking at that on our z table. So we have to go to this table again, and -0.1 down here. This would be 0.11, 0.12, 0.13, 0.14, 0.15, 0.16, 0.17. So it's going to be somewhere between 0.44038 and 0.43644. So if we round up, it's going to be, let's say it's closer to this, right? Let's say it's closer to 0.43644, 0.43644, according to our z table. So if we want to use our calculator, let's go to the calculator. So remember, second vars, go to normal CDF. The lower bound is 0 for 0-minute delivery. Upper bound is 30 for a 30-minute delivery. The mean for this one was 31, and standard deviation was 6. Do all that, we paste, and there you go, 0.433816. So very close to what we got from our table. Remember, our table, doesn't go out this many decimal places. From our table, we just rounded this to -0.17. So our numbers are a little off, but they're still pretty close together, right? 0.43381 versus 0.43644. Pretty similar. But now we're comparing them. So probability. So which probability is higher? Well, for the first pizzeria, the Lucas Pizzeria, this essentially is about 34% probability, 0.34 being about 34%. This one is about a 43% possibility. So this probability is higher than this one, meaning that Vinny's is more likely to get there in 30 minutes than the Lucas. So if I want my pizza within 30 minutes, I have a better chance of getting my pizza within 30 minutes with Vinny's time than the Lucas time. And I'm sure that's what all this is. So yeah, there's guys showing you how to use a table. Right, so that shows us, that basically just worked out the Lucas time. It didn't really do the same thing for Vinny's time, but it did give us the Lucas time, but you would repeat the same thing for Vinny's time. Down here. So there's Vinny's. So again, they used a table. They got 43%. I just worked all this out to explain it to you, but yeah. The comparison tells us that Vinny's is a better probability, so he should order from Vinny's if he wants a better chance of getting it within that range. Here's another video of normal distribution. I recommend watching that as well, just in case this video is too confusing for you. Page 3. Now, empirical rule. Okay, now this is about percentages, because we just talked about how these can be percentages. So when you look at a normal distribution, here's something I didn't add at the beginning, but I'm going to add in now. Let's use, can I make a different color? I guess not. I'll just use red again. So within one standard deviation, so basically this region here, from one standard deviation to the left to one standard deviation to the right, this is always, for a normal distribution, always about 68% of the data falls in that region. Why 68? Because that's just the way it calculates. But it's always 68% from one standard deviation within the region of one standard deviation, either to the left or to the right. Now, if you want to go out 2 standard deviations, so from here to here, and you're talking about that entire range, all in the middle, that now goes all the way up to 95%. So 95% of all the data is within 2 standard deviations. And if you want to go up even higher, all the way to 3 standard deviations, this is, I want to double check, but I think it's like 99, something close to 99. Does it say? Yeah, 99.7. So 99.7% of the data falls between -3 standard deviations to 3 standard deviations. So that entire region. So pretty much the entire curve, almost 100% of the curve or the area is within that region of 3 standard deviations. So all the way on the left here, this very small, or on the right, the very small bit on the left and the very small bit on the right, very, very minimal amount of data. Because almost 100%, right? Almost 100%, 99.7% falls within this region of the curve. So 68, 95, and 99.7 is kind of the rule to follow. 68, 95, and 99.7. General rule to follow. You have to kind of memorize those numbers because those numbers are for every normal distribution. All right, so that's what all this first part says here. Now, example 1. A number of candies in a bag is normally distributed with a mean of 32 and a standard deviation of 2. Let's make a graph for that real quick. So a mean of 32, so the mean will be in the middle, and a standard deviation of 2 means this will be 34, 36, 38, 30, 28, 26. So the mean here is in the middle. Our graph would look something kind of like this. So, approximately what percent of bags contain between 30 and 34 candies? So we're looking from 30 to 34 on our curve. So from 30 to 34 on our curve. Now you'll notice immediately that that's from 1 standard deviation to 1 standard deviation. From I guess the -1 standard deviation to +1 standard deviation. We're looking at this region from 30 to 34. Well, because it's from 1 standard deviation to the other 1 standard deviation, right? Between 1 standard deviation from the mean, I already know, based on the fact that this is normal distribution, that this is going to be 68% probability. Because it's within 1 standard deviation. If it's within 1 standard deviation, it's 68% probability. And there it goes with that rule again. Now, if you want the calculator to verify this, for those interested in using the calculator, go to second vars again, normal CDF. Our lower bound is 30. Our upper bound is 34 because we're going from between 30 to 34 candies. Our mean was 32 and our standard deviation was 2. That's all the information it gave us in the problem, right? It told us the mean was 32, the standard deviation was 2, the lower bound was 30, the upper bound was 34. And when I paste this, it'll be 0.68 something, right? There you go, 68% probability. The calculator verifies it. It's always the same, okay? But we don't even need the calculator because we already know the 68, 95, 99.7 rule. Keep that in mind. Finding a raw score. Emma knows that to get into her favorite school, she will have to earn a score that is at least 2 standard deviations above the mean on her college entrance exam. Assume that entrance exam scores are normally distributed with a mean of 650 and a standard deviation of 50. What score does Emma need on the exam to get into her school of choice? So let's make this graph that they've used. Okay, they've made the mean was 650 and the standard deviation of 50. So the mean is 650, and then 1 standard deviation is 50. So this would be 700, 750, and then 800. Down here would be 600, 550, and then 400. So there's your curve. Now, to get into the school that she wants, she has to score at least 2 standard deviations above the mean. So if this is the mean at 650, 2 standard deviations is here at 750. So she has to score higher than 2 standard deviations above. So she has to score higher than a 750. If she scores anything higher than a 750, 750 plus, she will get into her school. She will be accepted into her school. So that's exactly what that graph is saying. And there you go. So this example, a prestigious company claims that its president earns a salary that is in the top 2% in the nation. The salary in the nation is normally distributed with a mean of $49,000 and a standard deviation of $7,000. How much does the company president earn? So to do this one, let's make our thing again. All right. Okay. So the mean we know is 49,000. Standard deviation is 7,000. So it's going to be, what's 7,000 more than that? 56,000. And then another standard deviation would be 63,000. And then one more standard deviation would be 70,000. If we go down, it would be 42,000. Another 7,000 less than that would be 35,000, and then 28,000. So he makes in the top 2%. So that's going to be obviously way up near the top there, right? But this chart gives us a good idea of how to do it. Now, okay, if you're going to use the calculator, let's do non-calculator first, and we'll try it with the calculator second. So if you're not using a calculator, what we're going to do, top 2% up here means wherever this is, and I'm just putting a random line. It's not at 70,000, but we'll say it's around there, right? We need an area of 98% over here, right? So we need a z-score that's going to be equal to 98%. So when we look at our table here, let me see if I can go to the table. We're going to look for something of 98%. Oh, wait. Is it even on this table? Oh, it's on the next one. There we go. Okay. 98%. So the closest number we can find to 0.98 is 982, 981. Right here at 0.97982, because the one after that's 0.98030. So this number is slightly closer to 0.98 than the other one. So we're going to use that. So it's at 2.0 and then all the way up to 0.05. So this means that the z-score would be 2.05. So we reverse our formula. Remember, so 2.05 is the answer. But we have x minus the mean divided by standard deviation. Now, we know the standard deviation was 7,000. We know the mean was 49,000. So now we just work backwards and solve for x to find out exactly what the value of x was. So before I calculate that, let me go back and explain what we did. If it's in the top 2%, right, then because the way the z-score works is it calculates the area from the left side to the right side. It doesn't go backwards. So the reason why we're not looking for 2% in our graph is because 2% would be the bottom 2%. It'd be way down here. So we have to look for the bottom 98% since the top 2% is on the right, because that's the way the table is designed. The table that we're using, when I look at all these fancy numbers, it's designed to look at it from the left side to the right side. So if we're looking for the top 2%, then I want to figure out where the bottom 98% lives. So we're looking for the bottom 98% because we're going from the left to the right, not the right to the left. So I went to my table, like I said, and I looked for that 0.98. And the closest number I can find was right there. You can see where I'm clicking, right? And that number, when I trace it over to the left, is at 2.0. And then when I trace it up, 0.05. So when I put them together, 2.0 and 0.05 makes 2.05. So that's what I'm equaling this to. And then I go back to the formula I mentioned earlier about, x minus the mean divided by standard deviation. And I just plugged in my value. So now we're going to solve. So we're going to multiply by 7,000 on both sides just to cancel this out. So 7,000 times 2.05 is 14,350 equals to x minus 4,900. Or 49,000. So now we just add the 49,000 to the other side to cancel it out. And we end up with x is equal to 63,350 as our value. Okay. So now with a calculator, here's how this would work. It's a little bit different. When you go to second vars, you're going to click on inverse normal because now you're actually kind of working backwards. Inverse normal is what we're going to click on. We know the area would be 0.98% because we're looking for the top 2%. So the area here that we have to calculate is the bottom 98%, as I mentioned. Our mean was 49,000. And our standard deviation was 7,000. And then the tail is on the left because that's how it, like I said, this is standardized. It works from left to right. And then we just make sure that's selected, hit paste. And there you go, 63,376. So obviously very, very close to what we got. So that's perfect. So you can use the calculator or you can not use the calculator. It's up to you. If you have a graphing calculator, obviously this becomes a lot easier, but you can still do this from scratch by hand. So yes, it works it all through it here, but I just figured I'd explain it all in that video. Okay. Great Gummies has determined that a gummy bear measuring 1 inch has a z-score of +1 and a gummy bear measuring 1.25 inches long has a z-score of +2. What are the mean and standard deviation of the candies? I'm just going to quickly kind of show the work here and let it be said. So since there is one standard deviation from +1 to +2, we know the standard deviation is 0.25. I think that makes perfect sense, right? Because if it's 1 inch, it has a standard deviation of +1, but when it's 1.25 inches, it has a standard deviation of +2, which means between the two of them from +1, can I click on this? From +1 to +2, that right there means that these are one standard deviation away from each other, because from one standard deviation to two standard deviations is a distance of one standard deviation. So from 1 inch to 1.25 inches, that means the standard deviation was the 0.25. So they found the standard deviation of 0.25 just like that. They used the z-score to calculate the mean. So because they know that 2 standard deviations away is the value of 1.25. That's a picture. I can click on it. The value of 1.25 and standard deviation is 0.25. They plug those values in to find the mean. So they calculated the mean as 0.75. Again, if you need a little bit more explanation, let's say this. Let me draw it out for those visual people. So we don't know what the mean is, and we don't know what the standard deviation is. But we do know that at +1 standard deviation, it's 1.00, and at +2 standard deviations, it's at 1.25. So because that's one standard deviation apart, I can tell that the standard deviation is 0.25. So that's what we were saying before. Now for the z-score part, because this is 2 standard deviations away, right? That's our value, like the 2.05 last time. the plus 2 standard deviations is 2. We know that 2 standard deviations is 1.25. 1.25 is the x value. The mean is something we don't know yet because we're not sure what the mean is, but we do know the standard deviation was 0.25. So remember the formula, right? These are the numbers plugged in the formula. The formula is x minus the mean divided by standard deviation. Well, x at 2 standard deviations was 1.25. So that's why we can plug the 1.25 in there. And we know the standard deviation, because we just calculated it, was 0.25. So now you just do some math to find the mean. So they multiply both sides by 0.25 to cancel this one out. So that's going to be 0.5 equal to 1.25 minus the mean. And so now I'll just subtract 1.25 from both sides. That leaves us with negative 0.75 equal to negative mean, but then, of course, divide by negative 1 just turns everything into positive. So the mean ends up being 0.75. But you could have also kind of reverse engineered that, honestly. Instead of doing all of this work, if you know the standard deviation is 0.25, then this also would be 0.25. So if the mean is 0.25 away, then, well, 0.25 less than 1 would mean that the mean is at 0.75. So you could have calculated that way. It's probably actually faster to do it that way. But nonetheless, all of it is tied in. You can solve it more than one way, and there you go. All right. Here, this is just a helpful slide too. It's not a problem, but if you're curious about the z-score in the area, you can get the percentage from your z-score. So like, remember earlier we had negative 0.4 as our z-score. Well, there's your area, 0.34. It rounds it, but we said 34% probability, if you remember. We also had a z-score at 0.16, 0.17. And if you kind of roughly put it between negative 0.1 and negative 0.2, you get somewhere between 0.46 and 0.42, 42% and 46%. So this is just a little bit of a calculator, if you will, to kind of help you out. So you can use it as much as you want if it benefits you. Okay, but that's everything. I hope it makes a little bit of sense. If it doesn't, please just message me. I'll be happy to help. I know I kind of ramble on these a little bit, but I do the best I can. Good luck with everything this week. I'll see you guys in the next section. Bye.